Fundamentals of Electrical Circuits. Today we are going into the second session in power measurement. Okay? So power measurement, as you must have noticed in the first session, is very simple, except of course if you don't follow some of the guidelines that were given earlier. In this session as well, we'll be trying to look at again power measurement, and then we'll be focusing on single phase AC power as we did in the early case as well. But at the same time here, perhaps there might be small variations with respect to a concept, of course not with respect to the real concept, but some certain additional information might also come to you. Like for instance, in this circuit, though we did a maximum power transfer theorem based problem in the first session, here it is a little different because we are having two AC sources, okay, and there is a resistor in between, and the resistor in between has on either sides 6 ohm, 8J, and 6 ohms and 8J resistance reactance combinations on either side. Okay, both the voltages happen to follow the same phase because one is 110 angle 0, the other is 90 angle 0. Okay, and what is required? Let's see. Two AC sources feed a common variable resistive load as shown in figure under the maximum power transfer condition. Okay, so what is maximum power transfer condition? It tells us that it is equal to RL should be equal to the resistive value should be equal to the impedance that you get as the Thevenin's impedance. To get Thevenin's impedance, you short out the two sources, and then you go in either directions. In both directions, you see 6 plus J8, which is the same as equal to 2 6 plus J8 in parallel, or in other words, it is 3 plus J4, or the impedance is going to be a resistive value of equal to 5 ohms. Okay, please note that it is going to be resistive, no doubt, but its impedance, but its resistance value will be equal to the impedance value obtained out of a parallel combination of 2 6 plus J8 impedances, okay, or it is equal to 5 ohms. Okay, so that's point number one. Point number two is what is the Thevenin's voltage. Okay, Thevenin's voltage is also easily obtained because now if you remove RL, then you see that it's a single series circuit with 110 angle 0 minus 90 angle 0 because they are in the same direction. So 100 angle 0 minus 90 angle 0, which is equal to 20 angle 0, feeding the entire circuit. Okay, so and then so we feeding the entire circuit, and what is the circuit? It is 6 plus J8 into 2 because there are two impedances there. Okay? Or in other words, now the current is going to be equal to 20 angle 0 divided by 6 plus J8 into 2. Okay, or in other words, it is the same as equal to 2 into 10. 6 and J8 together gives you 10. 2 into 10. Okay, so 20 divided by 20, and the angle is going to be equal to on the denominator. That is the influence angle is going to be, as is always the case when it is J8 and 6, then it's going to be angle 50. That is you can find out the angle. Since the power factor is low, it's only equal to 0.6. The angle is bigger. That's equal to 53.1. Okay, so it's so now the current is the same as equal to 20 by 20, which is equal to 1. And the angle is going to be minus 53.1 because the impedance angle is on the denominator. Okay. Now this current drops across 6 plus J8 and creates a drop there. Okay. What is the 6 plus J8? It is the same as equal to 10 angle 51. Okay. 53.1. So the net effect is that there is a 10 volt drop. Okay, because minus 53.1 angle plus 53.1 angle is equal to 0, or in other words, now it is the Thevenin's voltage is equal to 100 angle 0, as is shown as point number 2. Third is of course the Thevenin circuit current. Now what is the Thevenin circuit current? It has 100 angle 0 as the voltage source, and then it has the equivalent impedance, which is 3 plus J4 because 6 plus J8, 2 6 plus J8 are in parallel, so 3 plus J4, and then you have that 5 ohm resistor. Okay, so in total the resistance is going to be 5 plus 3, and the reactance is the same as equal to J4. Okay, so 100 divided by 5 plus 3 plus J4 is going to be the Thevenin's current, which is the same as equal to 100 divided by, of course you can take out 4. Okay, as also you can take out it is going to be 8 plus J4, so you can take out 4, and then the remainder will give you root 5. So 100 divided by 4 root 5 is going to give you the current. Okay, and this current, when you square it and multiply it by 5, which is the equivalent resistance, okay, RL, which is equal to RL, then you see that the power is going to be equal to 625. Okay, So as a 4-step version, I hope it's clear to you that you find out the Thevenin's impedance. Okay, call it as 5 resistive value, 5 ohms as the resistive value. Okay, then find out the Thevenin's voltage. How do you do that? Thevenin, okay, you open out RL and try to find out what is going to be the drop across 6 plus J8. Deduct it from 110 angle 0, or you can go from the other side and you'll see that is same as equal to 100 angle 0. Okay, then Thevenin's current is the Thevenin's voltage source feeding 2 bits of impedances. One is 3 plus J4, the other is pure resistance 5 ohms. So you get the current, square it, multiplied by by R, which is equal to 5 ohms. You see that it's equal to 625 watts. The second problem, again we are having a statement problem. It says that the voltage V and current A across a load are as follows. Vt is equal to 100 sin omega t, and IT is equal to 10 sin omega t minus 60 plus 2 sin 3 omega t plus 5 sin 5 omega t. All the multiple frequencies, okay, that you are seeing here, 3 omega t, 5 omega t, do not matter at all, because you can't have intersection between the two quantities of voltage and current. Only the quantity that is going to be mattering is going to be 100 sin omega t as the voltage, okay, interacting with 10 sin omega t minus 60 as the current, and releasing a power as given by 100 by root 2 into, because they are maximum values, 100 by root 2 into 10 by root 2 into cosine the angle between them, because it is both are sine quantities, so the angle between them is 60, so cos 60, which is giving us a value as equal to 250 watts. Okay, so these are very important points that which I hope that you will remember all through. Okay, a similar problem is given here. The voltage across the circuit in the figure and the current through it. So what is the circuit? The circuit shows us that there's a current flowing into the electrical circuit given by IT, such that it has a voltage Vt across it. Okay, so IT into Vt is going to be the power. Okay, so let's see, Vt is given as equal to 5 minus 10 cos omega t plus 60 degrees, and IT is equal to 5 plus x cos omega t ampere. Okay, so there are two components for voltage as also for current. Okay, so yeah, and then what is omega is given as equal to 100 pi radians per second, which is not important in power, because omega happens to be the same for both the voltage and current if they are relevant. Okay, if the average power delivered to a circuit is 0, this is important. So the total power delivered to a circuit is 0, then the value of x in amperes is what? Okay, so the x is a constituent of the current IT as given by 5 plus x cos omega t. So there are two DC values, 5 and 5. Okay, so these two multiply together, and so there's no root 2, etc. So 5 into 5, 25 is going to be the wattage. Okay, so this 25 wattage has to be compensated, because this because the total power drawn by the electrical circuit is equal to 0. This 25 wattage has to be compensated by the power that is behaving in an opposite direction. Okay, so that's why the vector diagram is shown here, 5 and 5 together on the horizontal axis, as also we are having x cos omega t on the horizontal axis, because minus 10 is of course on the other side, minus 10, okay? And then it is also what is called as cos omega t plus 60 degrees, cos omega t plus 60 degrees. So that's the reason why plus 60 has been projected back, and now we have Vt as equal to minus, because the projection is taken into consideration, and then there's a maximum value 10, and then there's an angle of omega t is cos and omega t happen to be the same, so you just need to take the 60 degrees, which was earlier in the first quadrant. Now it has moved on to, now this component of voltage has moved on to the third quadrant. So now it's very clear that the power that is going to oppose the DC power of 25 watts, such that they get cancelled with respect to each other, and so the electrical circuit draws no active power, though it might be drawing reactive power, which is not expected out of us. We'll see that Vt has to be projected onto the horizontal axis, such that they happen to be in the opposite direction, that the current and voltage happens to be in the opposite direction. So now 25 is the same as equal to 10 from the voltage divided by root 2 multiplied by x, which is again the cosine component of the current, divided by root 2 multiplied by the angle between them, which is 60 degrees. So cos 60. Okay, so cos 60 is half, and so you can see that you can just solve for x. It is the same as equal to 10 ampere. Okay, I hope I don't need to repeat, but still I'll say the vector diagram is useful, but much more than that, the understanding that this electrical circuit draws no power, or in other words, the DC power is not going to be compensated with the AC power. Why can it compensate? Because the voltage and current happen to be in the opposite direction with respect to the AC component. Okay, because AC voltage component is minus 10 cos omega t plus 60 degrees, and current component, the AC component, is x cos omega t. Okay, so since they are both cos and both have the same frequency, we align them according to according to the horizontal axis reference. Okay, so we have 60 degrees in the anti-clockwise direction, which is projected back. So now we see that now the current and voltage are in the opposite direction. Okay, so because of minus 10, you're projecting it back. Okay, and so the horizontal component is taken, and now we are having power absorption, whereas in the other case it was power delivery. So we we can set 25 as equal to 10 by root 2, because 10 is the maximum value, into x by root 2, because again x is the maximum value and both are cosine, and so the angle between them is 60 degrees, so cos 60 degrees. Moving on to the fourth problem, the average power delivered to an impedance of 4 minus j3 by current 5 cos 100 pi t plus 100 amps is what? Okay, so it's very simple in the sense that we are having 5 as the current as the maximum value. So 5 square, which is 5 square is the current value, but of course you have to take by root 2, so 5 square by 2. Okay, because this is the maximum value, multiplied by 4, because only 4 consumes power. Okay, 4 minus j3, which only consumes power. So it's clear that answer B is correct, which is equal to 50 watt. Okay, moving to the last of the lot, let's see what's happening here. We are having a current coil connected to a load between R and Y, and we are having a potential coil Bn. Okay, so that's the requirement for a vector diagram. And what is asked out of us is that a single phase load is connected between R and Y terminals of a 450 volt source. Symmetrical 3-phase 4Y system with phase sequence R by B. Okay, everything as normal. Wattmeter is connected to the system as shown in the figure. Power factor of the load is 0.8. That's also given, lagging. The wattmeter will read. Okay, so wattmeter will read what it sees. Okay, it sees a current coil as given by 400 volt, because R by, so I have drawn R by here. We have VR, V by, VB. VR by is now at 30 degrees with respect to VR, and here we see that it is the lifeline voltage is already given is equal to 415. So 415 is the voltage. Okay, and what is the current? 415 is the voltage across RY, and the current will be given by division by impedance 100 ohms. Okay, so 415 divided by 100, that's equal to 415 by 100. But then what is the power factor angle? So the angle is, of course, the angle is with respect to the voltage that the load sees. Okay, so don't be confused there. Don't take any single phase situation, etc. The load is now connected across RY. So across V, so with respect to VRY, the power factor angle is 0.8, and 0.8 is always indicative of 6.9. Okay, 36.9. Okay, also it doesn't matter, it's a smaller angle, that's all. Okay, so that's also shown here, and that's with respect to VRY. Please remember that. Okay, and now we want to find out what is we want to find out the potential coil. The potential coil is across Bn, so we have taken B. Okay, and we have projected it back such that we can we have projected back such that we can see how the current and voltages are related. Okay, so we see that it's, and moreover we'll immediately say that the value is going to be negative, because we have projected back. Okay, because now between VB projected back and the current, we see that now there is an angle as given by, okay, of course, since it's projected back with respect to horizontal is 60, and then there's already an angle 30 degrees. So between the current and the voltage, now we are having an angle which is given by 90 minus 36.1 or something like that. So and its cosine value is now going to be not 0.8 but 0.6, the other quantity. Okay, when if the angle is 56, then you are having a power factor as given by 0.6. If the angle is 33, okay, but the 90 minus that, then it's going to be 0.8. Okay, so 415 by root 3 minus, of course, then because the voltage has been considered negative in this case, then minus 415 by root 3 show to give the phase voltage, because Bn is phase voltage, multiplied by 415 by 100, okay, to get the current, multiplied by 0.6, because as the new power factor, you see that the value is the same, is equal to minus 597. You can always take some average values and arrive at this value. Okay. Finally, the sixth problem, wherein we see that we have a voltage being measured, we have a source being given, wattmeter is there, okay, and we also have a load, okay, and what is given is, for the circuit shown in the figure, the voltage and current expressions are Vt is equal to E1 sin omega t plus E2 sin 3 omega t plus, and It is equal to I1 sin omega t minus phi1 plus I3 sin 3 omega t minus phi3 plus I5 sin 5 omega t. Okay, so in this case there are only two frequencies match. One is omega t and other is 3 omega t. So you can simply multiply them together, the voltage and the current, multiply them together, of course with the root 2 on the denominator of both voltage and current, and then with, take the cosine of the angle between them. So in the first case you are having E1 I1 by 2 cos phi 1 plus, okay, the harmonic is also creating a power loss which is measurable, and it's given by E3 into I3 again by 2 by root 2, so 2 by 2 multiplied by cosine of the angle between them, which is phi 3. Okay, so answer C is correct, and that brings us to the end of this session. Thank you.